Okay. Hi, everyone. Let's just start this lecture. So mostly today we are going to talk about cylindrical coordinates. Cylindrical and spherical coordinates. Okay, so the idea is that Cartesian coordinates, or these rectangular coordinates that we have been working most of the time, I mean all the time so far, it's only one possible way of labeling points in space. You can label points in space in different ways. And Cartesian coordinates, where you choose kind of orthogonal frame in some point in space, and you measure everything against that orthogonal frame, is only one method. So, but in general, you realize that to specify a point in space, no matter what method you use, you're going to need three numbers. But how those three numbers are going to be obtained depends on the method. So you have already done something similar, actually, in Calculus 1000 or one-variable calculus, maybe in high school, I guess. That is, so let me recall for you that early idea, which is completely similar. We had this, you had this idea of polar coordinates, right? So this is just a recall and warm-up for what is going to come in. So this is in 2D. Remember? Maybe you recall what was polar coordinates. So we have this xy. Of course, this is Cartesian coordinates. But then we said, okay, if I have a number, if I have a point here like P, which has coordinates x and y, I can equally specify this if I know this distance to the origin, like r, and the angle, theta. So P is x and y. This is in Cartesian coordinates. We can specify the same point P by these two numbers, r and theta. Same point can be specified by two numbers, r and theta, where the meaning of these two coordinates are now different. R is distance to the origin, and theta is the angle, right? R is distance to the origin, and theta obviously is this angle between this line segment PO and x-axis. And of course, from your basic trigonometric formula, you know how to find relation between xy and r theta, right? For example, here x, this is x. This x is r cosine of theta, right? X is equal to r cosine of theta. And of course, y is r cosine of this pi over 2 minus theta, which is sine of theta. You have seen this formula. R equal to sine. Okay. So these two formulas tells us how to go from Cartesian, how to go from polar to Cartesian, right? So from polar to Cartesian. these are these two formulas. X equal to r cosine of theta, y equal to r sine of theta. Now, you can go backward. If I have x and y, on the other hand, we can find r and theta also, right? So how do we find x and y? I mean, how do we find r and theta in terms of x and y? Well, I mean, here, for example, you know that r squared is equal to x2 plus y2, right? And we can divide these two things. So let me just maybe start by working with these two formulas. We have x squared equal to r2 cos squared of theta and y squared equal to r2, this is sine squared of theta. And we can add the two, you get x squared plus y squared equal to, since sine squared plus cosine squared is 1, so I get just r squared, right? So this is equal to r squared. You can say, okay, r actually, you can just take the square roots. You can just say r is equal to square root of x squared plus y squared, right? Now, to find the angle also, because r is not enough to find the angle, we can just divide these two, maybe y over x, and then I get y over, then r's cancel, and you get tangent of theta is equal to y over x, right? So if you divide, you get tangent of theta equal to y over x. So of course, from here, you can just say theta is equal to arctan of, okay, so I know I cannot write over there. So you get theta is equal to arctan of y over x, right? Okay, so these formulas, these two formulas, and this first one that we derive, are completely clear geometrically. Just from the geometry of this triangle, it's completely clear, right? But we just derived it algebraically also. So we have these two formulas. So we can go from, so the idea is that we can go from our theta to xy. You can think about it like this. From coordinate our theta, you go to coordinate xy. And also from coordinate xy, we can go backward to coordinate r theta. So it's just a two-way, right? And from xy, we can go maybe to r theta. And these two, okay, so these two operations are called coordinate changes or coordinate transformation. So we can go back and forth between these different coordinates as we choose. But this is all from one variable calculus. In this case, it's happening in 2D, and I just recalled it as a warm-up also. Any questions about this? Okay, so now we can go to what we have to discuss today. This is cylindrical and spherical coordinates. So let me go to, so I'm going to erase this here. So let me go now to cylindrical coordinates first. That's easier, actually. Spherical. Again. So now we are going to in 3D. So we have a situation like this. So I've got a point P. So we've got a point P. And so this P in this X, Y, Z coordinates has 3 coordinates in X, Y, Z, of course, right? So now what you can do, we can drop a perpendicular line and say, okay, this point P is really completely determined by this point, which is P prime. Now, the point of this point P prime is that it's on X or Y plane. That's two coordinates now, right? So we just use that. And then this Z, we just keep it as is. We just don't change this step. So let's call this now this distance, say R. The distance between the projection of P on X or Y plane to the origin, right? And of course, now I have this X here, and as before, Y here, and then Z here. Okay. So the three coordinates that we have, cylindrical coordinates, are these three numbers, R, theta, and Z. So how can I go from R, theta, and Z to X, Y, Z, to good old X, Y, Z? Well, I mean, here we can see that X is equal to R cosine of theta. As in polar coordinate case, Y is equal to R sine of theta. And Z is equal to Z, right? So these formulas you have to know absolutely. And these formulas are formulas for going from cylindrical coordinates to Cartesian coordinates. Okay, so from cylindrical to Cartesian. So these are these rules that we just find based on very simple geometric argument, essentially using polar coordinates. So for the first two coordinates, X, Y, Z, we are just bringing in polar coordinates. And Z, we don't change at all. Now, of course, from here, we can write we can find R, theta, and Z in terms of X, Y, Z backward. We can go backward too, right? So, for example, you know that what is theta? Theta is equal to R tan of Y over X, right? And what R is the square root of x2 plus y2 as before, and Z is equal to Z. Right? So this is from Cartesian to cylindrical transformations. Okay, so if we have these coordinates in one of the systems, either cylindrical or rectangular or Cartesian, we can just find the other one using these coordinates. Now, what is the point of using different coordinate systems, you think? What do we gain? Because it looks like we are making something more complicated this way. What do we obtain by this method? What do you think the point of this exercise is, in other words?
Depending on the problem you're trying to solve, it might be more appropriate to approach it with one set of coordinates.
Exactly, exactly. Yeah, so some questions might be more natural to do in cylindrical coordinates. So what kind of questions are more natural to do in cylindrical coordinates? It has to do with the idea of symmetry, right? Problems that have sort of cylindrical symmetry, it's better to move to cylindrical coordinates, and you can guess that the formulas are going to be simpler in that coordinate system. But if your problem, it's kind of completely alien to the idea of cylindrical symmetry, it's not a good idea to go there. You can use a different method, right? So let me give a very simple example, maybe working in back and forth between different systems. Any questions about this? No? Okay, very good. So now let me just ask some. Okay, I should have. No, that's okay. Actually, that's a good mental exercise to check that we remembered all the formulas. Actually, I have to check myself. So challenging myself, right? So okay. So here's a simple example. The equation. Say R equal to constant. What kind of shape? For example, 2, right? Let me put it like 2 instead of general constant. What shape it represents? That's a reasonable question. What shape R equal to 2 represents? I've got some questions, by the way. Okay, so there's an answer. Very good. Yeah, I have one answer from, yeah, the other. Yes. R equal to constant. Yeah, I know what you have in mind. This is for the next topic. This one is actually, sorry about that. Okay, this is my email system. Anyhow, so, but R, what is R? R, you see, measures the distance to the z-axis. So that's so because I said you drop and you do this. So this is basically your distance to the z-axis. So I have to draw it right in. This is R, distance to the z-axis. So if I say that the distance to the z-axis is constant, then it means what kind of shape is it? It's a cylinder. Right, exactly. It's a cylinder. So this is a cylinder. Okay, this is the cylinder. You can say even more. It's a cylinder. It is a very special kind of cylinder. You remember there was an issue about cylinders, right? From last lecture. A cylinder is not a tube, just a tube. A cylinder could be more general than just a tube. It could be like, as you know, at some angle with, for example, XY plane, and it could be its base could be just a general curve. That's also a cylinder. But here is a very nice cylinder. So the z-axis just goes through the center of the cylinder, and this is like x, o, y. So this is the z-axis. Yeah. So this is the cylinder. Now, can you write this equation in Cartesian coordinates, for example? R equal to 2. What would be in Cartesian coordinates? That's a reasonable question, right? Yes?
It could be anything.
Could be what?
Could be anything that R equals 2, like you don't know what the x and the y.
Yeah, but what is the, but yeah, that's right. But we want to write the equation of the surface in Cartesian coordinates. Yeah, that's right. X and Y could be anything, but they are tied. Yes.
Like x would be 2 cos theta, y would be 2 sine theta.
No, that's right. But in your equations, you're not supposed to have. If I ask go to Cartesian coordinates, you should not have any r and theta. You should write everything in terms of x and y and z. How do you write this r equal to 2 in terms of x, y, z? Right, no, you should not have 2 cosine of x, 2 sine. No, sorry, that's not correct. This is a surface. So we should get the equation of a surface in Cartesian coordinates.
Like x squared plus y squared equals 4.
Yeah, that's absolutely correct. Right. So so r equal to 2 in cylindrical. So remember, what was the formula of going from cylindrical to Cartesian? R was square root of x2 plus y2, right? So we have to replace that by square root of x2 plus y2. But I know that this is 2, right? So as it was mentioned, then the answer is going to be x2 plus y2 equal to 4. So these two equations, they define the same geometry, same shape, same surface. This is in Cartesian coordinates. Right? So now you notice this equation is more complicated than r equal to 2. Of course, r equal to 2 is much easier, right? I mean, it's just r equal to 2. It's kind of deceptively easy, actually, because you just say r equal to 2. So that's but x2 plus y2 equal to 4, it's there's more algebra there, right? There's more. So this might help, actually, in big time as we move on. Okay, so let me ask another question. What about then the equation theta equal to constant? So equation theta equal to, for example, uh, 3 pi over 2. What shape?
Would it be like a plane that's parallel with the z-axis?
But half plane only, right? It just happened because we start from just half of the story, right? Exactly. So this is indeed, you see, if you have just in xy plane, it's a plane, but be careful, it's a half plane. Yeah. And I expect you to tell me which plane is it, actually. It's one of the coordinate planes, it's half of it. So this is xy. If you want to have 3 pi over 2, you have to come back here. So when you look at it in 3D space, so that's x, o, y, z. So you move here pi over 2, you get pi, and then here is going to be this one is theta equal to 3 pi over 2, right? So this is pi over 2, and this whole thing is 3 pi over 2. Right, so this is. So how do we describe this in Cartesian coordinates? So you have to be careful, right? What is the equation of this surface in Cartesian coordinates? And we know that it's not going to be a full surface, full plane, right? It's going just to be half of it. But first, let's keep the equation of this plane in Cartesian coordinates. What's the equation?
Y equals x multiplied by tan of 3 pi over 2.
Again, we should not have any tan or any r in our equation. We want to write everything in terms of Cartesian coordinates, right? So we should move. I have one answer. I acknowledge that answer. Yeah, very good. But that answer has to be, yeah, okay. Now, okay, right. Good, it's corrected, right. So, and I have to come down as well. Okay, so the answer really is, first of all, we know that x is 0, right? But it's indeed a half plane, but y is not positive. This has to be less than or equal to 0. So that's the only condition. And y less than or equal to 0. So that's the equation. that corresponds to theta equal to 3 pi over 2. Of course, we can use more complicated formulas. If I told you that, for example, theta is equal to pi over 4 or something, we would use really like relation between x, y, z. So we have to be careful about these things, and otherwise, I think things are okay. Any questions so far? Yes.
What exactly do you mean by half plane? And also, and another question.
Right.
Like, how does theta equals 3 pi by 2? Like, how did you get that in 3D?
Here?
Yeah, like, how did you get
Right.
that?
Yeah. Okay. So let me start from your second question. How do we get theta equal to 3 pi over 2? You see, what is if you look at here, theta is really the angle that's measured in x or y plane, right? So if you just want to do 3 pi over 2, you have to come here, right?
Yeah.
So that's the other half of the y-axis that cuts down. Okay. So, but now we are in 3D space, but that's okay. This is x, o, y, z, and in 3D space, all these vertical directions are just added because we are in 3D, so there's no difference. But essentially, what really matters in terms of angle is when you project down, you measure in x or y plane, and that's it.
Oh, okay.
Yeah, there is a little bit of maybe you have to orient yourself, imagining something like that. You get it? Very good. Okay, so this is 3 pi over 2. But now your first question, you had also a very good first question. Why is it called a half plane? It is a half plane because if I just said x equal to 0, that would be really a plane, right? That would be just yz plane, x equal to 0. But we are not considering all of that plane. The way that this polar coordinate is just goes through this half direction all the time. So here is specified by also noting that y is less than equal to 0. So that's the half plane.
Oh, okay.
Yeah, that's is it clear? I have one question. No, I mean I had good answers, right? Very good. Okay, very good. So that is as far as cylindrical coordinate goes. I mean, okay, so it's a good idea to write down equations of all those surfaces in cylindrical coordinates. Also vice versa. We'll do some of those through these assignment questions and also exercises. There are a lot of questions related to that in list of suggested problems. Do you guys try suggested problems at all? Yeah, they're quite useful. I mean, that guides you through the kind of literature on this. I mean, concepts, really, not literature. Okay, so now another coordinate system, which is a bit more different now from polar coordinates, although it's quite similar, is spherical coordinates. So let's tackle that now, spherical coordinates. So what is it? This time, we are going to actually say, okay, I have a point P in space. Again, this is my Cartesian coordinate axis. So I'm going to, the first thing I'm going to use is this rho. So my first coordinate is going to be rho equal to distance to the origin. That's rho, as you can see. Right? That's distance to origin. And then there is an angle here which we can use, phi. Another coordinate we use is phi. So angle between PO and this z-axis, I would say positive z-axis, and positive z-axis. Okay. Okay, then what we can do, we can use another angle to be the polar coordinate of the projection. So let's project this down. Let's call this prime P prime. Project the point P orthogonally on X or Y plane. And let's use this angle, theta. So, and finally, theta is angle between, this is really polar angle between OP prime and the x-axis, right? Between OP prime and x-axis. Okay, so so we have three sets of coordinates: rho, phi, theta. You can also write rho, theta, phi. It doesn't matter. I mean, you can write them in any order you want. That doesn't matter. So we have these three angles, but what is important is that you understand geometrically the meaning of these angles, and also notation for them is fixed. So for phi, please don't use theta or psi or I or something. This is written on stone. This is phi. Okay, it's not negotiable. Theta also not negotiable because it's polar and whatever is used. And rho also is almost fixed. Anyhow, so we use these things. But now the question is how we go from rho, theta, phi, knowing this is the definition, to x, y, z, right? And backwards. So knowing, I mean, x, y, z, I mean, for example, let's start now. For example, what is x? How can I find this coordinate x of the point P to this rho, phi, and theta as they are defined here? How can I define them? Well, I mean, look, what we have is that x is equal to OP prime, right? Times. Can you tell me what is x in terms of OP prime and theta? Cos of theta, exactly. X equal to OP prime times cos of theta. Okay, so this theta is good, but OP prime, still I have to write it in terms of rho, theta, and phi. How do I write OP prime in terms of rho, theta, and phi now? How can we do that? Well, look, what is OP prime? OP prime is OP cos of this angle, right? That's again by. So that's equal to OP times cos of. So let's call this angle theta prime, for example, because we don't know what it is yet, times cos of theta. Okay, but still, theta prime is not in my list. I have to write everything in terms of theta, phi, and psi. What is the relation between cosine of theta prime and this? What is the relation between theta prime and this angle? Put this in theta prime and phi. What's the relation between the two? Class, what's the relation? Yes, exactly. They add up to 90 degrees, exactly, right? They add up to 90 degrees. So I can say cosine of theta prime is equal to sine of phi. Right? That makes sense, right? So that's equal to, but OP, I know what it is. I call it rho. So I just say this is rho. So I've got rho sine of phi. So this is sine of phi. And then we get cosine of theta, which is cosine of theta, times cosine of theta. Okay, so this is the first line. X is equal to rho sine of phi cosine of theta. That's what we discovered by this simple geometry. Now, again, we just continue. Y is equal to OP prime times what? Because now we are talking about Y. This is Y now. So what is Y? OP prime times sine of theta, obviously. So times sine of theta. But now OP prime, so this is again, I just continue here. This is OP prime. So this is OP cosine of theta prime times sine of theta. Finally, it comes rho, but this is the same as before, rho sine of phi cosine of theta. Okay, that's good. And what about Z? After all, what is Z? Because we have to know what Z is, right? Z is equal to rho cosine of phi. Oh, I forgot to. Sine of phi, what? What's the question?
Oh, I was wondering about that.
Oh, right. Oh, this is, I'm sorry, this is sine of, here was sine of theta. This is sine of theta, yes. Thank you for noticing that. Yes, sine of theta. Okay, good. Now, what about Z now? What about Z? How can I write Z in terms of X, Y, in terms of rho, theta, and phi? Z. Well, you see, Z, again, is equal to rho times cosine of phi. That's it. This is, again, you're using the same idea, right? Z equal to rho cosine of phi. Okay, so now let me write this list of transformations here because we know the definitions of these angles. It's a good idea to keep them in one place shorthand. So finally, so what we got so far is that, okay, so this is sine of phi cosine of theta. So we have got X is equal to rho sine of phi cosine of theta. Y equal to rho sine of phi sine of theta. And Z is equal to, we just draw rho cosine of phi, right? So as before, now these are transformations between, yeah, that's correct, right? These are transformations between, transformations from spherical coordinates to Cartesian coordinates, right? So this is spherical to Cartesian. So these three things, either you should memorize them or you should be able to drive them immediately on demand, but that's not difficult. You can do that, I suppose. So it's a good idea to remember those formulas. So that's this direction. Now, we can go backward as before, right? How can we go backward? Well, I mean, the geometry tells it all, right? So let me erase this then. For example, what is rho? Rho is equal to a square root of x2 plus y2 plus z2. So this is the square root of x2 plus y2 plus z2. I mean, this is the distance formula after all. I mean, you don't have to know anything to know that the distance is given by square root of x2 plus y2. This is Pythagoras' theorem, right? So now, what about, so how can I find now phi, for example? Well, look, phi, that's very nice, because here I can just solve for cosine of phi. Is z over rho. So that's equal to z over square root of x2 plus y2 plus z2. This is cosine of phi. If you want phi, you have to apply our cosine function to that, right? So this is equal to our cosine of z over square root of x2 plus y2 plus z2. Right. Now what about theta? So what about theta? Okay, to find theta, we can do the following. We can divide the first two equations. For example, divide this by second by that. You get here so what I'm saying is that divide 2 by 1, we get y over x is equal to rows cancel, sines cancel, you get sine of theta over cosine of theta, which is tangent of theta. So that's very nice. So theta is equal to tan inverse of y over x, which is arctan. So theta is equal to arctan of y over x. Good. And these are then equations for going from Cartesian to spherical. Now, there are several things we have to know about the range of these values. I mean, they are not completely random, right? For example, rho cannot be negative from the geometry also, we know. And so the range of phi, can you tell me what is the range of phi according to the geometry of the problem? What range phi can change? Yeah.
0 to 90.
So you're neglecting lower hemisphere spherical people for Australians?
So 0
to
180.
180, yeah, exactly. It's 0 to 180. Yes, absolutely correct. It's 0 to 180. So let's remember phi is between pi and 0. What about theta? What is the range of theta? Any yes? Yeah, I've got answers. Yeah.
0 to 90.
Again, you're neglecting a lot of people in the universe. Yes.
0 to 2 pi?
0 to 2 pi, yeah. That's like as before. 0 to 2 pi. Because this theta goes all the way around. There's nothing to start. We have to cover that. We have to cover in order to cover the whole space. Otherwise, we're just covering quarter of the space or half of the space, But theta has to be between 2 pi and 0. And rho, of course, is bigger than. So these are the appropriate ranges. So range of coordinates theta phi rho. Spherical coordinates theta phi rho. Now let me do one problem which I think is kind of nice. It shows some. So let me ask you this question then. Any questions so far about this? Okay, so let's now do, so I'm going to erase this actually. So I'm going to give you a hint. I'm going to tell you this is a surface. You see, before I didn't commit myself to being a surface, or I just said shape in order not to direct you toward the right solution. That was a bit of mischievous choice of words, right? But I'm going to tell you this is a surface. What surface is given by the equation the equation that I have is rho equal to sine of theta sine of phi. So obviously this is a relation between theta, phi, and rho. Any relation between theta, phi, rho is generically a surface, as before we had a relation between x, y, z. This was a surface also. So here is a surface again. But what kind of surface is generically is a surface? I mean, it could be a point, it could be empty set, it could be a line. But generically, any equation between these three variables is representing a surface, generically again. So whatever generic means, which I don't tell you. Okay, so we have to do some calculation, right? We cannot just do it by looking at it. We have to do a calculation. I mean, this is not something like before that we can. So what we have to do, we have to use these formulas, for example, this formula, to replace rho theta phi by an equation in terms of x, y, z. So let's do it, solution. Turn this equation, because honestly, it's very hard to imagine this equation in spherical coordinates and guess what kind of equation is it, what kind of surface it's representing. I mean, by itself is not very illuminating, right? We have to turn it into something more illuminating. So the idea is, solution is turn this into a Cartesian equation. So I gave you a hint. Can you try to do it, to turn it into a Cartesian equation? In other words, turn it into an equation between x, y, z, so that then we can just, perhaps we can see with what we know from last lectures what kind of shapes or surfaces. Okay, so here the equations are like here, for example. It's good to exercise now, yeah, to do this. Please try to do it. Yeah. Okay, perhaps you noticed that we should use the second equation, right? Which is y equal to rho sine of phi sine of theta, because this really appears here, sine of phi sine of theta. Okay, so this equation then, so let me call it a star. So if you use a star, you get rho is equal to, well, what is sine of phi sine of theta? Is y over rho. Okay, so this tells me that rho squared is equal to y. But we know what rho squared is. Rho squared is x2 plus y2 plus z2, right? So this is x2 plus y2 plus z2 equal to y. Now, can you tell me what kind of surface is represented by this equation? x2 plus y2 plus z2 equal to 1. This is from last lecture. You should be able to do it on the go. I mean, doable with what you know from last lecture. That's what I meant. Spherical. Yeah, I believe this is correct, but I have to see it. I don't know exactly. I have to check. Yeah, I believe this is correct. But how did you find it? Is it just because we cannot guess? We have to know exactly, right? I mean, you can guess. It's a good idea to guess all the time. But we have to prove. Well, how do you approach this question at all? Yeah.
Well, it kind of looks like a spherical equation if y.
Except that y is not 1.
Yeah.
So, but you can reduce it to that form. So this is one of the tricks that's kind of relevant from last lecture. It brings to the left-hand side. You just write x squared plus y squared minus y z squared equal to 1. As I said, you can complete this square now. So you get x squared plus
How is it equal to
0, 0. That's all. Sorry. Okay, so we've got x over y squared minus. Okay, so now this complete the square, you get y minus 1/2 squared minus quarter plus z squared equal to 0. So we have got x squared plus y minus 1/2 squared plus z squared equal to quarter. Right? So you can see this is a sphere, but its center now is shifted to 0, 1/2, 0, with radius 1/2. So it's a sphere with center at 0, 1/2, 0, and radius r equal to 1/2. Yes.
Where did the x squared plus y, where did that equation come from?
This equation?
Yeah.
Yeah. So we just we agree with this equation, right?
Yeah.
So, but then what is rho squared? What is rho? Remember what is rho?
Yes.
Rho is the square root of x2 plus y2 plus z.
Oh,
So
okay.
rho squared is x2 plus y2 plus z. Right. Very good. So, okay. Let me read some of the answers. Sphere centered at 0 minus 1/2. Oh, minus 1/2, be careful. No, yeah, you corrected. 1/2 answer. Yeah, ABC is, yes, that's right. And so a sphere at that center, but then with radius 1/2. You should also specify its radius. You know that, right? Spherical, yeah, that's so we had a couple of good answers. Yeah, thank you.
How did you get the radius to be 1/2?
Oh, what was the equation of the sphere? X minus a squared, right? Plus y minus b squared plus z minus c squared equal to r squared, right? So r squared is a quarter, so r is 1/2. It's always a square, right? It's like a circle in the. Okay, yeah, good question. Thank you. So yes, okay. So any questions or comments? I mean, we are already 5 minutes. Okay, guys. So let me just stop the recording. But I'm here. I will send some announcements today regarding office hours and TA issue.